Alright, in this video we're going to talk about integrating factors. If you are watching this video and you are not up to speed with exact ODEs, please do first watch our video on exact ODEs before you continue with this one. Alright, so what are integrating factors? Well, if we start with an ODE, so suppose the ODE m dx plus n dy equal to 0. So suppose this ODE is not exact, okay, meaning that my is not equal to nx. Okay, now for some ODEs, it is possible to find a function mu. It is possible to find a function of x and y mu and this function is such that if we multiply this ODE, let's call it 1, then the resulting ODE is exact. Okay, so often it is possible to find a function mu such that if we multiply, so mu times m dx plus mu times n dy equal to 0 is now exact. Okay, so when we multiply 1 by mu, we get equation 2, but equation 2 is an exact ODE. Okay, so it is possible to find a function mu such that this new equation is exact. What do we mean? So if you take the coefficient of dx now and differentiate it with respect to y, it is going to be equal to the coefficient of dy differentiated partially with respect to x. Now the function mu is then called an integrating factor. Okay, so the function mu is called an integrating factor. So basically an integrating factor is a function which is such that if you multiply your ODE with a function, the new ODE is exact. So mu is an integrating factor. All right, I'm going to consider two somewhat special cases for the purposes of this video. So we consider two cases. So in case 1, we consider the case where mu is a function of x only. Okay, so this is going to happen if my minus nx over n is a function of x only a function of x only, then the integrating factor mu of x is given by the exponential of the integral of my minus nx over n dx. Okay, so this is the first case. So let's call this one equation number 3. Okay, then case 2 is a case where our integrating factor is a function of y only. So in this case, if nx minus my divided by m, if this is a function of y only, then our integrating factor mu of y is going to be given by the exponential of the integral of nx minus my over m dy. Let's call this one equation number 4. Okay, so those are the two cases we are going to consider in the examples that follow. There is a derivation of how these come about, but we're not going to cover that one in this video. All right, so let's look at some examples now of how this works out. Okay, so here are some examples. We're going to want to solve each of these 3 ODEs stroke IVP. So the first one has got an initial condition, so that's the IVP. The other two are just going to find the general solution. So let's get on with the first one. So the first thing we're going to do is we're going to write this one in the I shall call it that standard form of m dx plus n dy, which is given in equation 1 here. So everything is on the same side. So here, since 2xy dy is on the left hand side, we're going to bring it to the left hand side equal to 0. So that means our m is 2x cubed y squared minus x, and our n is negative 2xy. Now, so if we have not been told anything about this, and we are not necessarily doing it under the section of integrating factors, first thing we're going to look to do is to see whether we can separate variables here. For n, you can factor out x and y, but for m, you cannot factorize this. So that means the equation is not going to be separable. So let's just say m cannot be factorized. So that means the equation is not separable. Separable equations is one of the forms of equations of ODEs that we've looked at. Moreover, m is not homogeneous, because as you can see, the powers of x and y are varying here. 3, 2, and 1 there. So M is not homogeneous, so that means this equation is not homogeneous. And then the next thing we're going to try is to see whether my is equals to nx. So here my is 2y, nx is negative 2y. So that means they are not equal. Okay, so just because of that negative, so ODE is not exact. All right, and then so now we're going to try these two forms. So we're going to try and work out this combination. If this combination is a function of x only, then we can find an integrating factor. Or if this combination is a function of y only, then we can try, we can find an integrating factor. So first we're going to try my minus nx all divided by n. So my, we've already said, is 2y, and then minus nx, so that's going to be plus 2y because it's negative. Then n is negative 2xy. So that means we're going to have 4y over negative 2xy. So this is going to be negative 2 over x, which is a function of x. So that means this is fitting under case 1 here, because this combination is a function of. So we can now use equation number 3 to find the integrating factor. So mu of x is going to be the exponential of the integral of negative 2 over x dx. So if we integrate this, integral of that is going to be negative 2 ln x. So this is going to be e to the power negative 2 ln x. And so if we simplify that, it's just going to give us 1 over x squared if you use the properties of natural logs and stuff. Now so that means if we multiply this equation here by 1 over x squared, it should become exact. So let's see how that works out. So multiplying the ODE by 1 over x squared gives, all right, so that means going to multiply this by 1 over x squared, and that everything by 1 over x squared. So that's going to give us 2x plus y squared over x squared minus 1 over x dx minus 2y over x dy equal to 0. So that is our new ODE now. So so this time this is now our new m, and this is our new n. So let's see if this is now exact. So if we do my, this now is going to be 2y over x squared. If we do nx, this is now going to be derivative of negative 1 over x is going to be negative 1 over x squared. So the thing is going to be now plus 2y over x squared. And indeed, my is now equal to an x. So which is exact since my is equal to an x. And so once it's exact, then we can use the methods that we have seen. So it means there is going to be some function f which is such that its partial derivative with respect to x is equal to 2x plus y squared over x squared minus 1 over x. Its partial derivative with respect to y must be equal to negative 2y over x. From the first one, okay, so let's say integrating the x derivative is going to give us f equal, so integrating partially with respect to x. So the first term is going to integrate to x squared. This one is going to integrate to minus y squared over x. And the last one is going to integrate to ln of magnitude of x. Then this is going to be plus some function of y. Then we're going to differentiate this with respect to y and compare with this equation here. So if we integrate this with respect to y, we get negative 2y over x plus phi prime. So if we compare these two, we can see that phi prime must be equal to 0 because there is no other term here. So if phi prime is 0, it means phi is equal to k. And so if we just plug in k here, so therefore x squared minus y squared over x minus ln of mod x plus k equal to 0. So that is our general solution. Okay. But for this ODE, or given an initial condition, so we're now going to apply that initial condition. Initial condition says when x equals to 2, y is negative 1. So when x equals to 2, y is negative 1. Right, so we're just going to plug that, and that's going to tell us what the value of k should be. So plug x is 2 here, going to give us 4. Y squared is 1 over 2, which is x, minus ln of 2 plus k equal to 0. So this is telling us that k is equal to ln 2 minus 3.5, which is 7 over 2. And then we're going to take this and plug it in there, which gives the particular solution. So that means our particular solution is going to be x squared minus y squared over x minus ln 2x is equal to 7 over 2. Right, so that sorts out the first one. Let's now go to the second one. So in the second one, in part B, we have x squared y squared dx plus 2x cubed y minus 7y squared plus 4 over y dy equal to 0. Again, if we try to factorize here, we're not going to be able to factorize. So that means this equation cannot be separable. This equation as well is not homogeneous, so that approach is not going to work. Is this equation exact? Well, let's see. So here m is x squared y squared, n is 2x cubed y minus 7y squared 4 over y. So my is going to be 2x squared. Yes, so my is going to be 2x squared y. Nx is going to be 6x squared y. And so since those two are not equal, it means this ODE is not exact. And then what we're going to do is we're going to try the same thing we tried with this one. So we're going to see if the quantity my minus nx over n is a function of x. So let's see. So my minus nx over n, my minus nx is going to be this minus this. So that's going to be minus 4x squared y divided by n, 2x cubed y minus 7 y squared plus 4 over y. Okay, this one is going to be a bit of a problem to try and simplify. As you can see, I've already said that this one is not factorable. So that means this one is going to just be a function of x and y. So it's not going to give us any help. So let's try the other combination, nx minus my over m this time. So the numerator is now going to be 4x squared over y. Denominator, remember, m is x squared y squared. Okay, looks like some terms are going to cancel out this time. So this is going to work out actually to 4 over y, which is a function of y only. So that's good, because it means this is fitting in the case 2 scenario. Okay, so that means we can find an integrating factor. Let's see how that works out. So therefore mu of y is going to be the exponential of the integral 4 over y dy. This is going to be e to the power of 4 ln y. This is going to be y to the power 4. That means y to the power 4 is our integrating factor. So we expect that if we multiply the ODE by y to the power 4, the resulting ODE must be exact. Okay, so if we do that, the ODE is going to be x squared y to the power 6 dy plus 2x cubed y to the power 5 minus 7y to the power 6 plus 4y cubed dy equal to 0. This is our new m, this is our new n. So my is now going to be 6x squared y to the power 5. Nx is going to be 6x squared y to the power 5. So that means the ODE, the new ODE, is now exact. If that is the case, it means there exists some function f such that yes, so there exists a function f such that its x derivative partial is going to be equal to our m here. So it's going to be x squared y to the power 6. And the partial derivative of this function with respect to y is going to correspond to our function n. So that's going to be 2x cubed y to the power 5 minus 7y to the power 6 plus 4y cubed. Okay, then integrating the equation for the derivative of x is going to give us x to the power 3 over 3. Yes, so integrating that gives x cubed over 3 y to the power 6, and then there's going to be a function of y. Then we're going to differentiate this with respect to y and compare with the y derivative, which is this one here. So if we compare those two, you can see that these two terms match up. So that means these other terms must be equal to phi prime. So phi prime is going to be negative 7 y to the power 6 plus 4y cubed. So phi is going to be negative y to the power 7 plus y to the power 4 plus k, and so the function or the solution is going to be a third x cubed y to the power 6, which is this one, and then simply plus the phi function equal to 0. So this is the general solution. All right. Okay, so at this point, we're going to give you the opportunity to have a go at C. So just work through C. You can pause the video, and then when you press play, then you can compare with our solution. All right, we hope you have now had a go at C, let's just scroll down to our solution here. All right, so for C, you're going to find that if you try to factorize, you won't be able to factorize here, so it means the equation is not separable. These terms are clearly not homogeneous. And then if you try my and nx, they are not equal. But if you work out the quantity nx minus my, this is what we have. Multiply through everything by y cubed gives us these two terms, and then if you factorize, then you can see that this term is going to cancel out, so we've got 2 over y, so that is a function of y only. So this tells us that the integrating factor is going to be y squared. So multiply the ODE by y squared. This is the new ODE we get, which is such that my is equals to nx. So this now is exact. So that means there is some function f such that its y derivative is y squared plus 2x. If we integrate that with respect to x, then we're going to get xy squared plus x squared plus a function of y. And if we differentiate that partially with respect to y, we're going to get 2xy plus phi prime. Compare this with this, then that tells us that phi prime is actually minus 3y squared. So phi is going to be k minus y cubed, and so the solution is going to be x y squared plus x squared minus y cubed plus k equal to 0. So that is going to be the solution. Alright, so thanks for watching this video. If you find the videos useful, please do subscribe so that you can get notified whenever we post new material.